Module 24, Non-linear regression, multiple regression and logistic regression. Section 1, Non-linear regression. Non-linear regression fits the non-linear models with the data. So just like simple linear regression, but in the case of simple linear regression, it's only simple, that is linear data, but here it is non-linear data. So unlike the linear regression that can fit only one model, that is a linear equation, non-linear regression can fit any other models or any number of models, and therefore it's more general, it's parameter rich and it's more general, while simple linear model is only just one, it's a very simple model. So non-linear regression can be thought as an extension of linear regression, but mathematically this method is far more complicated. So in fact, the linear regression is a subtype of non-linear regression. There are several subtypes of non-linear regression. Linear regression is one of the simple subtype where the equation is, the lines, simple straight line equation is being used for simple linear equation. For an in-depth understanding of how non-linear regression works, understanding of matrix algebra, as in the case of the principal component analysis explained the last module, and calculus is required. So we are not coming to the complexities on how non-linear regression actually works, but we will just say the most important characteristic how it works in later of the same this module. However, to perform this non-linear regression is actually a matter of few clicks. Any of the software like GraphPad Prism can easily perform this non-linear regression with a model of your choice. For example, an equation, for example, the Michaelis-Menten equation of the enzyme kinetics is your non-linear model, and how good your data fits into that model is what is being tested in this non-linear regression. So what is the difference between linear and non-linear? So of course linear has the linear equation, that is y equal to mx plus c, but in the case of non-linear it is not, obviously it's not a straight line. And linear regression doesn't have much utility in biological sciences, because a number of models in biology are non-linear. For example, bacterial growth rate and or growth curve, dose response in the pharmacology, or enzyme kinetics. All these are non-linear models. So you can consider the Michaelis-Menten equation of the enzyme kinetics. The equation is like this: y is equal to Vmax into x divided by Km plus x, which is not a linear equation. You see, it's a curved equation. So if you have this kind of data, first of all, if you're working with enzyme kinetics, so on the x-axis you write the x-axis is all about substrate concentration, while y-axis is all about the reaction rate. So how fast the reaction happens when you increase the substrate concentration. So first of all, you put the dot plot, and as you can see in this dot plot, nothing is obvious. Then you will try to fit a straight line to it. Well, a straight line fits kind of, but it's kind of a very loosey fit, and you can generate r square and then try to interpret the data. That is totally wrong. So if you already know that what you're working with is the enzyme kinetics, then probably the best approach would be, instead of fitting a straight line, you will go straight away with Michaelis-Menten model and try to find a fit. As you can see here, this model, the Michaelis-Menten model, fits much better than a straight line model. So that is how you are actually doing that. Another example here is a bladder muscle relaxation. So for example, norepinephrine in millimolar versus percentage urinary bladder muscle relaxation of the rat. Rat tissue is what is being produced here. So it is actually x and y variable. There are two variables here, and the x variable, the norepinephrine concentration is expressed in log. It's log transformed scale. So how do you actually use this one? So in this case, we have to decide the model. So it is not automatic, or the computer cannot decide or generate a model for you. No, you have to decide a model, and you are now looking whether the model is fitting well or not fitting well. That is what you are looking at it. So model is an equation, non-linear regression model. There is no such a one equation fits for all. Everything has got, every data has got its own equation, which is not linear though. For dose response, usual model is that y is equal to bottom plus top minus bottom divided by 1 plus 10, to the power log EC50 minus x multiplied by Hill-Scop. That is the formula that is being used here. So bottom means value of y when x is very low. So usually it is 0, it need not be, depends upon the biological context. So in this case it is 0, because if you do not put any norepinephrine, then relaxation, you can always say that it is 0 relaxation. Top means value of y when x is very high. So if the x is very high, what is the maximum value of the y? So that is what is called top. Now log EC50 means value of x when y is half maximum of the y. So maximum y, the half maximum, at that time value of x is called EC50. Hill-Scop quantifies the steepness of the curve, hill and slope. So hill slope, that means how steep the curve is. So all these are the parameters of this non-linear regression model. So how does it works? So that is why it's quite complicated. I'm not going to mathematical, but in summary, non-linear regression uses matrix algebra and calculus. It is an iterative process. It generates initial curve, and step by step this curve is refined to minimize the sum of square distances from all the data point. So it just draws the initial line, then iteratively it actually makes this fit more and more easier. So sum of square is minimized. So this the line fits very nicely the data, and when it becomes worse, it just stops and reports the previous best value. So that is how this non-linear regression works. So it is an iterative process or computer expensive process. So it's basically highly computational process, something like bootstrapping, which we explained when we explained about the confidence interval. So this is also an iterative process. So that is also an iterative process. So this is this too. So in nonlinear regression, there are a set of assumptions, just like in the case of linear regression. And this set of assumptions are almost identical except the first one. The model is correct. Of course, if you are going for a non-linear regression, the model, if the chosen model is inappropriate for explaining this non-linear regression, then definitely it won't work. So the model is correct is the most important assumption for this non-linear regression. And the independent variable x has no variable, x axis has no variable, all variability is in the y axis. The independent variable is x while dependent variable is y, so all variability is in the dependent variables. The scatter of the data around the curve is Gaussian, the homoscedasticity. There is equal variance everywhere throughout the line, from one side to another side, the variance remains identical. Data points are independent, and x and y are not intertwined. All these assumptions are identical to the linear regression. So the main output of the linear regression is a curve fitting all these data point. The curve is basically the model which we said. So whether in that model, what are the parameters, so that the regression model will find the best fit parameters of the chosen model. So that is what it is, the non-linear regression is all about. So the tabular result will have the most important characteristics is like it depends on which equation that you use, but the parameters, all of these parameters, for in this case EC50 is there, hill slope is there, all these parameters, what is a best fit number, best fit values that will be given to in this research section. And also the R square, the R square is a regression coefficient, so that will also be given to will be presented in the result section. So if the regression, as you know, if the R square value is closer to 1, means it's really good fit. So in this case it is 0.99, which is really good fit. So that is what how to interpret these results of this nonlinear regression. So nonlinear regression model could be anything. So one of the simplest model is, which I told you, it is a linear equation. Next simple model is polynomial model. So polynomial equations are also quite mathematically very simple. So y is equal to c plus mx is linear equation, while y is equal to c plus mx plus m2x square. So that is basically the second order or quadratic equation, which is the simplest polynomial equation, which will produce this kind of parabolic output. the graph. So by the way, if you want to graph anything from the equation to generate the graph, so you can use a number of online websites, you know, for this purpose. So interesting calculators are available. For example, Wolfram Alpha is an excellent graphing calculator, so you can generate this kind of graphs. So the another kind of thing is with the cube in it. So y is equal to c plus mx plus m2x square plus m3x cube. So that is basically the third order equation or cubic equation, another type of the polynomial equation. So polynomial regression can be used, but unfortunately this kind of polynomial regression don't have much applications in biology. So biological systems tend to be a lot more complicated, so we really need more complicated nonlinear equations. So what are the mistakes in nonlinear equations? So nonlinear equation is very easy to do, but interpretation and whether to choose the right model, these are really trouble for an uninformed gentleman, you know, the scientists. So one of the common mistake is that transforming curved data to the linear form and using the linear regression. So this kind of transformation to the linear form is incorrect, you know. So for example, the double reciprocal Lineweaver-Burke plot in the enzymology. So earlier days, before the advent of the computers, the enzymologists used to actually you know, convert this non-linear form to the linear form, and then after, you know, to generate the plot called Lineweaver-Burke double reciprocal plot, and after that they back convert that into the non-linear form. So this kind of normalization is invalid and there is no need of it. We don't really need to work with a graph paper and ruler and a pencil. We have a computer. Even the most basic computers can do all this graphing, you know, the non-linear regression calculations quite easily. So letting the computer program to choose a model, that is incorrect. You have to choose a model based upon the data that you are having in your hand. Fitting the rolling average or smooth data is incorrect. Using unweighted nonlinear regression when the scatter increases as y increases. So there is a non-homoscedasticity assumption. You have to use a relaxed model to accommodate that you know, violations of the homoscedasticity. Using R square to assess the fit is useful or not. No, R square doesn't say that the utility of the fit. It only says that how good the fit is, the R square value, but it's not, the usefulness is entirely a biological question that only a scientist can answer. You can also use this nonlinear equation to compare two models. For example, in this one you can see that the standard model versus the model where Hill-Scope has been set into 1. The standard model is the one, the nonlinear equation that we used. And if you actually, you know, if you constrict that equation to get rid of one of the parameter by putting a fixed value to it, that is 1 to the Hill-Scope, you are going to generate the dashed line. So as you can see, the dashed line is not fitting properly. The solid line is fitting much more nicely. And this fit is more easy to decipher by looking at the plot where the residuals are plotted. So you can see that on the right side is the you know, the fit of the you know, the a more constricted model where Hill-Scope has been put into 1. So as you can see that it is not really fitting perfectly. The residuals are varying too much. So in summary, unlike the linear regression that can only fit the linear model, so non-linear regression can fit any models and therefore more general. Non-linear regression generates a dot plot of the data with the best fit curve superimposed. R squared and Hill-Scope of summary table are the most important results. Usually the non-linear regression do not generate a p-value, while the linear regression do generate the p-value. Polynomial models are mathematically very simple curves. However, these models are rarely useful in biology. Thank you for watching.